Joe Pusztay is a postdoc here at the University of Buffalo. Over the course of the last few meetings, we've been able to kind of track the progress that he's been able to make on DMSwarm and applications using it in kinematic physics problems. And I think we have another update on that today. So let's see. No, you don't need to connect into the HDMI. You just need to screen share if you can. Okay. Yeah. So we've got on the boards the credentials.
Good.
Do we need your audio? I guess we're going to mute you either way.
Muted. Video off.
Share.
Share. Cool.
All right, go right ahead, Joe.
Thanks. So today I'm going to be talking about DMSwarmRT, something a little bit different that I've been working on a little bit, implementing into DMSwarm. So a while back, we were reached out to by the Laboratory for Laser Energetics, which is an NNSA facility located about an hour away in Rochester, where they do inertially confined fusion plasmas at the Omega Laser facility. So what they have is essentially a warehouse-sized laser that they break up the beam and route it around a spherical target chamber, and in the middle of that target chamber is your fuel pellet. It's a tiny little spherical ball of like frozen whatever they decide to make their fuel pellet out of with a exterior coating so that they get nice and uniform pellets, and then they study the ways different fuel pellet shapes and stuff interact to hit it with the laser, get the best atmosphere possible, deposit a bunch of energy into it, drive an implosion, and out pops fusion. But what is interesting about this problem is that you have all different types of parameters that you can try to tune to get better fusion production. One I already mentioned is like how they design their fuel pellets. Won't get into that at all because I actually really don't know very much about that anyway. And the other thing that they can control is the lasers. So there's all these different what are called beam ports around the target chamber, and they can tune the way that the laser comes out of those beam ports, so they can try different frequencies, they can try different phase shifts of the laser so that they can try to get it to traverse the ablative plasma atmosphere that forms around the outside of the fuel pellet when it gets struck. As soon as it gets struck, you get an ablative layer of plasma that forms around it, and it can reflect and refract the laser beams as they try and drive all that energy into the implosion, and you can get odd features that form like poor energy absorption and this part is particularly interesting. I won't get too much into it today because we're not there yet, but something called cross-beam energy transfer where beams within the same region can actually constructively or destructively interfere, and you transfer energy between the different beams. So a bit better view of that target chamber. We have on the left a diagram and unfortunately it's cutting off my citation from John Morozis. So I got this from a John Morozis paper. He is one of the scientists I'm working with at LLE along with Tim Collins. But in this paper, he goes on and discusses the current procedure that they have for doing ray tracing in a code called Draco. It's a very, not very old. It's a pretty old export-controlled code that does hydrofusion with a ray tracing component. So what they wanted to do is they started wanting to leverage GPUs for the ray trace. So they came to us and said, like, hey, could you help us get our ray trace onto GPUs? And I was interested in the project because, I mean, ray tracing sounds fun. And to be honest, beforehand, I really didn't know too much about it beyond RTX on, RTX off memes. So I said, we said, sure, we'll help you get that in there. The first kind of idea that we had was, well, what if we just try and wrap everything they do up in a PETSc and then we can just do some offloading using the backend kernels. But the more preliminary reading that I was doing on this, I realized that, well, we can have something a little bit more general. And we can cook up essentially a general purpose ray trace that we can apply to all different areas, because as I was finding out, there's applications to seismology, tracking P waves as they traverse through the crust. There's applications to astrophysics, looking at gravitational lensing with Hamiltonian optics, using symplectic, trying to use symplectic integrators for whatever their formulation of their fields are, traversing light through that, which has analogies to other areas of something called a GRIN medium, or for gradient refractive index medium. There's certain types of lenses in that case that have what are called optical black holes, which can have analogies to actual black holes when looking at gravitational lensing. So after talking to them for a while, we decided, like, why don't we just use all the tools that we have and try and build a general purpose ray trace, and then I will give you an API, and you can perform the ray trace for your specific experiment through that API, so that way, all of your export controlled stuff can stay, where it belongs, because don't want to get in trouble there. And then with my stuff, I can go and I can look at things like gravitational lensing and whatnot, and we can build a tool for more scientists to use within the PETSc framework. So at the heart of all this, and I'm going to go with their formulation of, it left full screen, and that's why we are cutting off. Yep, there we go. Perfect. Sorry about that, didn't realize that it left full screen. But I'm going to go along with the way they express their ray equations. But there are direct analogies to Hamiltonian optics. So for instance, when I'm going to discuss like the curvature of the vector and the direction vector here in just a moment, I'll also point out what can correlate to the variational formulation, where you derive a Lagrangian. From Lagrangian, you can get the Hamiltonian, then you can describe it as the characteristics, or you can get the characteristics of the system and describe it essentially as a kind of like a particle in a potential. But here at the base of it, everything starts with the Eikonal equation. We have up here at the top where we have the refractive index that we're traversing, and we seek the solutions which describe the paths that will be taken by the rays through that field of through that refractive index. So the ray equation is described here as the gradient of the index of refraction is equal to the derivative with respect to the differential path length s times the gradient of refraction, dr ds, where dr is our position vector and ds is the differential path length that we're going to be taking over that step. So we get dn ref ds, dr ds plus n ref dr squared ds squared. So with a little bit of rewriting, just kind of group the different derivatives together. We get the gradient of refraction with the description in terms of the curvature and the direction vector. So direction vector t here is a unit vector which describes the motion over, or the change in the coordinate of the ray over differential path length, and the curvature, which is described by the direction vector and the gradient of the refractive index at the point that we're evaluating the ray trajectory at, where refractive index is, in this case, 1 minus the normalized electron density at that point. So this is a specific thing to the ICF problem because we're thinking in terms of plasma atmospheres, so electron clouds. But this can generalize to any material, any function that describes our refractive index. So an approximate solution to this form with a truncated Taylor series expansion gives us a simple description of how we're going to actually time, or I say time discretize, and it's also used this way in the literature. I guess it's just kind of a habit where time is really referring to the differential path length, so delta s. So if I'm marching my ray by delta s, that kind of goes into the integrators and where time would be typically. So I'll say with respect to time, there is no time. Time is essentially actually frozen when considering these ray traces. So this gives us a decent way to approximate the solutions to the ray trajectories based on nothing more than being able to calculate the curvature, which remember is based on the gradient of the index of refraction at that point, which we know, and its position and where the ray is pointing at that time. So this gives us a 7-element system of ODEs. I kind of just slipped an element in there because I haven't mentioned it yet. But in terms of a typical integrator, or when looking at just general gradient refractive index materials, you would have 6. You would have your position, and then in the general case, for the Hamiltonian optics problems, you would have something called optical momentum. In this case, we have 7 elements. We have the direction vector, the position, and then this d tau. So what I mentioned earlier about the energy being deposited into the plasma so that you can drive fusion, there is this d tau term which can correspond to 2 things. In the simplest case, you have a mechanism called inverse Bremsstrahlung absorption. So as your beam traverses the plasma, it's depositing energy into it across the regions that it's traversed. So you integrate that over the differential path length with respect to the index of refraction at that point. That's that C located at the bottom. So a bunch of constants, the temperature of the plasma, a Coulomb logarithm in there, and then this NE crit. So we'll get to what NE crit is momentarily. That refers to the critical surface of the plasma. So that's a region where the plasma atmosphere has a plasma frequency that matches the frequency of the laser, something funky happens. But essentially, you need to accurately integrate the path length over these regions so that you can accurately calculate the amount of energy that's transferred from the laser to the plasma in those regions to actually be able to predict what is going to happen. In the case of ICF codes, a tiny little perturbation in that energy absorption coefficient will result in essentially a completely non-physical result, just from that tiny little perturbation being amplified by the rest of the hydro portion of the simulation, right? So some of the things that PETSc already had that were nice for getting this implemented, we needed the precise location of the cell where the ray exits cell faces so that we can know precisely where it exits. So TS event was really useful for being able to get that implemented quickly because it can do a bracketed route find so that we can set the ray trajectory and reset the steps so that it's right at the face or right over the face that the ray crossed over. Another future concern for this specific problem is the crossbeam energy transfer, but we're not there yet. That's a little bit extra work, so I'll probably discuss that.
I want you to give a talk that does your work justice, but just looking at your slide number left, you've got like 10 minutes left.
Oh yeah, we'll get through there. It's a lot of pictures.
Okay.
So I cut 10 right before I started too. But so basic procedure is pretty simple. It's actually not too different from what we already do for solving the Poisson equation for kinetic plasma simulation with our particle and cell approaches. We can use the DMSwarm for essentially holding all of the ray information. We use TS for whatever solver we want to use, our K4. I'm looking at using the symplectic integrators. I've got the split Hamiltonian formulation in, just haven't run them yet. Started doing that a little bit recently to try and get the generalization to the Hamiltonian option, or Hamiltonian optics. But this is essentially the recipe for everything that occurs in the TS event function. So as I mentioned, using DMSwarm to store all of our rays so that we know where they are in our domain. A DMPlex is managing the mesh topology so that we can use the Plex partitioner to match the partitioning of whatever external library is calling our APIs so that we don't have to have anything funky interacting with the code. TS event for bracketed route finding. And then something I'm just going to briefly mention at the end is the PETSc device. I'll say up front, I should probably call it PETSc, PETSc device backend to build a TS device, which I will say up front, I should probably rename to TS batched, just because I think that might be a more applicably descriptive name. So I've been talking a lot about how we're going to actually manage these solvers. Let's start looking at some examples. So one of the lovely things about the iconal equation is that there's no real analytic solutions except for in very few select specific cases. So your hands are tied when you want to have an analytic solution to compare to directly, and LaTeX compiled out my references. Awesome. But this comes from a paper that I will show the actual citation for at the end, I guess. But one of the cases that does have an analytic solution is an electron density trough. So you have a trough in your electron density field, so it's less dense in the center, more dense at the ends. You set the endpoints to be the critical surface density so that it can't escape from the trough, and you get a sinusoidal oscillation in the ray trajectory as it traverses the distance of this trough. This is a little heinous, but I have a qualitative comparison to the analytic solution here. Matt's going to tell me I really need to get that in at the end of this talk, because he said this after the last time I showed these. But the exact solution is on there. It's just covered by the markers. Numerical quantitative comparison is much needed and soon coming. So again, just check and verify that it actually works. So this time we're not operating on the CPU, we're operating on the device with some HIP kernels that I wrote for running on a Radeon 6900 XT. And whilst 1024 is not using the GPU very much at all, to the point it's really not doing it properly, the HIP trace is still a little bit enlightening in the amount of mem copies and synchronizations that are occurring just naively writing a HIP kernel into a TS right-hand side function to dispatch the computation of the curvature vectors at these points. So this was a bit of a motivating factor for the TS device, which we'll discuss at the end. So I'm going to skip that because I have only a couple more minutes. Some additional test cases where you actually have an analytic solution are with a 1/r² electron density profile, where you set the rays such that they have a varying impact parameter with the center of your density profile. So what you get out of that is the turning points for the rays should remain on the plane that they are initiated on, which they are. So this is a 2D projection this is an RZ projection of a fully three-dimensional ray trace on a spherical mesh. You get a parabolic shape that comes out of where the ray's turning points are in regard to their impact parameter. Now, on the right-hand side, I have a plot that shows what happens when you run this and the initial initiating rays are on a plane that is slightly shifted off-center. Everything is perfect because it never reaches the critical surface. And that is why the right-hand side looks a little bit better, because I haven't fully implemented critical surface handling, which in the generalized case is really an interface where the material is going to have a feature that causes a rapid change. So in the case of the critical surface, it may not be uniform, it may not be uniform across a cell, it might be shifted. So I'm still figuring out how exactly I want to handle that critical surface, but that middle ray should reflect exactly backwards, but is able to cross and enters a region where the solution is non-physical. The ray should not be there. So that's the next step, a next step here, which will also be good for cases where we have materials that rapidly change. A generalized example that I wanted to get in was the Lundberg lens, where you have just no electron density profile or anything. You just have an index of refraction profile defined by the square root of 2 minus r² over r, where capital R is the radius of your spherical lens. And I spent like 5 minutes on this last night. I was able to get some qualitative characteristics out of it. However, Matt just helped me right before my talk get my DM to refine properly so that I don't have an icosahedron, I have an actual ball. So we're not able to get, in my test case last night, I wasn't able to totally get to the end where the rays exit the lens all along a parallel line because they leave the face of the icosahedron, and that's where the ray trace terminates because they left our medium. And then I guess I will skip the TS device for now, but I will leave a parting word on the matter. So the idea is that we have all these rays that are traversing the mesh, and they need to have a bracketed root find to find exactly where they cross the zones of our cells so that we can accurately calculate interactions with the medium that they're traversing. In the case of ICF, that is directly energy deposition, how much energy they leave in the mesh. That causes us to have to do a TS reset so that every time something crosses the face of a mesh, we reset the time steps so that the ray can be accurately tracked. However, that applies to all of them. There isn't a reset or time tracking for individual elements of a TS. So I thought a neat idea would be to build a TS that batches up these rays and launches them in batches on little lightweight sub-TSs that run completely on the device so that each individual element can have its own time, its own event function definition, and even its own integrator. So just a silly little example demonstrating that it works with the event functions that I was writing. Is just launching a bunch of balls in the air and bouncing them off the ground. Not a thorough test, but make sure the event function works and it scales to 65,000 balls. So when I have a more interesting problem, I will scale it further. Thank you.
Thanks, Joe. Time for one question, maybe? Mark.
So your ultimate goal, or it sounds like the last one is sort of at least close to the ultimate goal of having them all being asynchronous, right?
Yes.
And they can all go. So you said you put it on the device. Does that mean you explicitly put it like groups of them on an SM then, and or they're just going independently, and so they're all the particles are independent?
Yeah.
So and there's really no synchronization. So you've got like 65,000 particles, say, on a GPU or something. So many more than SM. So you've got lots of them per SM, but they're really all completely separate. They're reading maybe the mesh, but they're all depositing energy on the mesh, right?
That does get into one thing that is still on my to-do list, which is implementing the mechanism that they know when to stop, right? So the real goal is that you can have, say, something like 56 ranks, which have 8 GPUs on that rank, but then another node that has its own GPUs, but all partitioned evenly so that I need to get a way to get the mesh in and support the mesh and the partition.
Like, so right now, the balls are
so right now, there's no real domain control
I see
at the moment. That is the ultimate goal.
Them all being really independent.
Yeah.
And they can read the mesh and see when they cross over, but then they are going to have to deposit their energy on a mesh, right? So you're going to need sort of synchronization at some point for that, I guess.
Yes.
Yeah.
Okay. Just trying to understand.
Yeah. So my initial idea for that was that everything can just store what it does in its local cells in an array, and when you go to do a migration between MPI ranks, you can copy that back to the host and assign it to a mesh cell.
And you have atomics too.
You have it depends, I guess, how often you're depositing them. And another thing we talked about was, it's kind of like a COO thing. You just emit a stream of deposit, and at the end you run over your deposit stream and aggregate to the cells. Right. So
I'll disassemble so we can get on. I think I'm taking up time.
Well, thank you one more time. Will our next speaker come up?